All right,
Hello.
Sachit, you can go ahead and get it started,
Yeah.
maybe.
Okay. All
So
right.
probably you
So
can
it's
go ahead and introduce the speaker and then get
yeah.
started.
Okay. Hi, Professor Alleyne. My name is Sachit. I'm the secretary of the Bangalore chapter of the Control System Society. So it's my pleasure to have you on this webinar. And given that it's also fairly early in the day for you in the US, maybe to our attendees, I'd just like to briefly introduce our speaker. So I can see that he is currently the professor at UIUC, and he also is a fellow of both the IEEE and the ASME. So he looks like he straddles all disciplines of engineering, aerospace, electrical, etc. I also see that he's greatly interested in teaching, given that he's the head of the undergraduate programs in mechanical engineering and science. And apart from his research interests, he also seems to be taking a very great interest in teaching and teaching the undergrads. I mean, there are numerous awards and other fellowships that he's obtained. He's also held several visiting professorships in both in Europe and in other countries, as well as being on several government boards in the US. If I'm not mistaken, Professor Alleyne, hadn't you come to the Indian Control Conference last year?
I
You had?
was 2019, I think.
It was in Delhi, right?
Yes.
Yeah, okay.
Professor Vijayasegar had invited me, and so
Yeah, I think I remember having seen you there. I was just there for a day, so I really
oh,
couldn't
okay.
meet anyone. Yeah. So it's over to you, and we'll be excited to listen to your talk.
Well, thanks.
Well,
Thanks very
I
much for
just
having
I
me.
just add a one line. I just add a line that he's also the one of the members of the IEEE Board of Governors. That's
Ah,
how
okay.
I came to know about him.
That is. Um, uh,
All right.
uh, well,
Get
well,
get
thank
started.
thank you very much. Thank you very much. I think all of those things in the introduction mean that I have a lot of gray in my beard these days. I've been around for a while and have had the opportunity to work with a lot of interesting and fun people and learned a lot and had a chance to contribute in IEEE. And so I'm grateful for the opportunity to be one of their distinguished lecturers and give a talk here on the control of complex energy and power systems. Um, I say for electrified mobility, what we're going to focus on here today is mostly in aviation, but I did alter the title a little bit to say electrified mobility because I want to make the case that what we're going to show here in aviation has impact not just in aviation, but in all kinds of mobility, terrestrial, marine, et cetera, et cetera. And we can go into that at the end on the Q&A if you wish. Um, so this is what I am going to be talking about today. Start with a little bit of a motivation, some modeling efforts that we've done. And I like to think that the way that we go about modeling these systems is kind of sort of unique, and it really helps enable some of the control stuff that we do later. Then we'll do some control design and show an example, and finish off with how we are working to integrate design with control, and then wrap up with some conclusions. Over there on the right, I'd like to show some of the students, current and former. I think all of these here are former students, and these three are current. And they've all sort of worked in this space and have all been great to work with them. They're at different places. These two, he's a professor at Penn State. He's a professor at University of Texas at Dallas. He's at Northrop Grumman, Ford, Raytheon, and Ford. Oh, and he's a professor also in Texas. So excellent people to work with. And why do we care? Let's talk about just the air case for now. If you look at the amount of power that goes on a given vehicle, aircraft, starting, back here in 1900s over sort of the course of the last 100 years, the amount of power has increased, and this is a log scale, roughly. It's just increased, I wouldn't necessarily say completely exponentially, but definitely superlinearly. And from one generation to the next, if you go from, say, the A380 to the 787, there's almost a doubling of the amount of power, electrical power that you have on board. And there are very good reasons for this. It increases efficiency is one of the big ones in the commercial space. In the non-commercial space, it gives you capabilities that you might not have without increasing that level of electrification. I'll talk a little bit in a couple slides about people that are actually trying to see if we can do electric propulsion for aircraft and kind of sort of get away from the internal, the Brayton cycle type of gas engine. But this increase in electrification is why we study electro-thermal types of control design. A big thing is once you actually start putting more power into these systems, what you really care about is the power to weight ratio in the case of aircraft. For terrestrial applications like cars and trucks and stuff like that, sometimes it's power to volume ratio, but those are both in the sense of power density. And once you actually start packing power more densely into a smaller and smaller space, what ends up happening is you, because of resistive heating, you can actually overheat your systems and for lack of a better term, just basically burn them up. And so it's important that you design and operate your electrical systems with the thermal systems together. It's for folks that are not in this space. Folks in this space understand that the thermal management is a key limiting factor to the electrification. Folks who are not in this space, I'll tell you, it's not just the electric motors and the power electronics that make the EVs, electric vehicles, run around. It's also heavily dependent on thermal management that you can put through these systems. So with that big demand over a long time, and I have slides on ships, on cars, on trucks, on bulldozers, on, you just look at, electric bikes, bicycles. There's all been this monotonic increase in the number, the amount of power each one is carrying, et cetera, et cetera. The federal government, the U.S. National Science Foundation, we were fortunate enough to stand up a center, which is the Center on Power Optimization of Electrothermal Systems. It's the center that I run as a director. And the goal there was to increase the power density using a systems approach. I'm a systems guy, and so it was natural for me to take a systems approach to this. One of the things that I found was that many people that were taking a shot at trying to solve this problem were solving a piece of the overall problem. They're solving a subsystem and figuring that if they solve their subsystem piece very, very well, and left it up to somebody else to figure out how to integrate it with somebody else's subsystem piece, everything would be fine. What we found is you can get more if you're integrating the subsystems at a system level than if you just did each one individually. There's 4 universities. University of Illinois is the lead institution, along with the University of Arkansas, Stanford University, and Howard University in Washington, D.C. And in sum total, there's about 35 projects running at any one point in time. We've got about maybe 60, 70 postdocs and grad students, maybe about 25 faculty, maybe about a dozen different companies that are involved directly. And the federal funding, it's about $40 million over 10 years. We went through the first 5 years, 2015 to 2020, and now we're into the second 5 years. In this first 5 years, we've also brought on an additional $15 million in external contracts and are ramping up and some others. And you can see the kinds of folks here. Many of these people you don't necessarily associate with electrification. We've been in discussions with all of these. We have sort of had projects and had memberships with all of these OEMs, except for Cummins. We're still in discussions with them. Then there's also several suppliers that you can think of that we've had detailed discussions with, and some small businesses and the government, NASA, Air Force Research Labs, Department of Energy, Navy. And we're really growing this ecosystem of government, OEM suppliers, and small businesses to try and take a look at this power density using a systems approach. And when I say systems approach, it's not just the control systems that I'm going to talk about here today. It is also the materials systems. It is the electronic design for the power electronics. It is the machine design. It is thermal management from the mechanical perspective. It is microfabrication. It's a whole bunch of things that we have to do to try and make the systems approach work. But the sort of the reason for doing this, I'll see if we can make it work. This gives an example from one of our partners here, Raytheon. And now it was United Technologies when they joined. It's a tech demonstrator. I think it's called Project 408 or something like that, where you're trying to replace one of these engines here with a hybrid electric system and a battery pack. And so the hybrid electric system, as you'll see, runs one of the engines part ways. And this is a technology demonstrator to see, before you go to full electric, if you can actually do hybrid electric. And the hybrid electric itself has some advantages. So you should be able to hear sound, I hope. Let me know if you can hear the sound on this.
You can put a little more volume, maybe.
Yeah.
Very, very little.
Today's regional aircraft use a 2-megawatt class engine.
Yeah, better.
The engine runs at full power, then levels off to 1 megawatt during cruise and descent. The Project 804 engine also delivers 2 megawatts of power in a 50-50 split between a 1 megawatt engine and a 1 megawatt electric motor, working as a parallel hybrid electric propulsion system. At takeoff, both the engine and motor run at peak power, together delivering 2 megawatts of power. Leveling to cruise, the electric motor throttles back, while the engine continues at 1 megawatt optimal performance for the full flight. Traditional engines are fully optimized, but have limitations that are well understood. Changing the game with hybrid architectures opens an entirely new optimization space, and opportunities we are studying for in-flight energy recovery can mean even more efficient performance.
So that just gives you an idea of one of the folks that are looking in this space. There's several other companies that are working in this space. And the federal government too. I don't know how many of you are familiar with an organization called ARPA-E, which is an organization within the Department of Energy. But they are focused on trying to see how you can push the envelope for energy-related technology, either energy production or increased energy efficiency. And one of the programs, they are really pushing this electrified aviation hard. Dr. Ohadi, Michael Ohadi, they started a program earlier this year called Ascend, Aviation Class Synergistically Cooled Electric Motors with Integrated Drives. And what they're saying here is that if you want to have the motor that you were talking about that was in that hybrid electric, what you'd like to have is you need to have the electric motor and the power electronics. So we call these the machines and the drives, tightly integrated with the thermal management systems, because if you don't, again, these things will overheat. Even on the power electronics, if you're 95% efficient, right, but you have a megawatt of power going through there, okay, that's still 50 kilowatts of heat that you got to get rid of. And that's a fair bit of heat. If you don't get rid of 50 kilowatts of heat, the temperature can rise really, really quickly till when the system is not functioning anymore. And so to make this overall system here run, you have to integrate the thermal and the electrical piece together, and that's critical. And Dr. Ohadi is putting his money where his mouth is. Just on motors and drives, they're putting in about $35 million US to try and accelerate that. And what they're trying to do is, if we look at the efficiency of the electric motor and the efficiency of the drives, sorry, not efficiency, the power density. Look at the power density, this is watts per kilogram, and the power density of the motors, this is watts per kilogram. You know, we are about here in terms of power density. You can do about 5 kilowatts per kilogram, maybe 6 or 7. And for these sort of efficiencies, they're at about 20 kilowatts per kilogram. I can say within our center right now, individually, we have come up with systems that are about 50 kilowatts per kilogram on the drives, and about 13, 14 kilowatts per kilogram. So we're out here somewhere in POETS. But to get to something that is sort of competitive for decarbonized aviation, we're really going to have to get up into this upper right-hand corner here, where we're looking at the overall drives and machines and drives are sort of in the 16, 15, 16 kilowatt per kilogram area. And we're not quite there yet. One of the things I will say, this is sort of a lot of electrical engineering and mechanical engineering, but the control part is a really important critical enabler. And I want to show you sort of how it's a critical enabler now before we get into control design. And there's a whole bunch of sort of background that we can go through if you want on a lot of the prior stuff that I showed. For these types of systems, I just showed you just one piece, where I showed you the electric motor and the thermal management system and the power electronics that have to be integrated. If you look at an overall vehicle, the energy domains that are in there are varied. You've got chemical energy conversion, you've got mechanical energy conversion and utilization. You've got electrical power distribution, as I just showed you, had been increasing. And so if I'm going to model these systems, I need to have an approach that can span multiple physical domains easily, must be modular and scalable. Models must be easily reconfigurable. And the reason why you want modularity and scalability is that you design a new aircraft, for example, once every, 20 years. And so you spend a lot of time doing concept development in the early stage. Right? And so you want to be able to go ahead and mix and match components pretty quickly and pretty easily without having to rip apart your simulation and model and sort of reconfigure it all over again. Additionally, after you have your models built, those go along with the aircraft. Aircraft last for a long time, but they get upgraded periodically. So if you want to go ahead and be able to plug in a new component where you've upgraded your aircraft into your existing one, you'd like to be able to just plug one piece of your overall system model out and plug in the new component and see how it's going to evolve. The models also should be accurate, obviously. And most importantly for this talk, those models have got to support control design and design optimization for these relatively complex systems. So the way that we choose to go about modeling these things, and there's a lot of history behind why we've done it this way. We represent the system as an oriented graph with vertices and edges, nodes and interconnections. It's very conducive to control development, as I'll show in just a second. And at the back end of the talk, I'll tell you about how it accommodates design optimization tools. It is by nature modular, and we use conservation laws to sort of focus on understanding how the energy flows. And the flow of energy from one vertex to another vertex is the power that's carried along an edge. And so each sort of rate of change of energy in a given vertex is basically the sum. So the rate of change of energy modulo the capacitance is equal to the sum of powers flowing in minus the sum of powers flowing out. And so the capacitance is store energy, as you can see here, all right? And the edge is transfer energy, okay? And we have some limitations on this in terms of the energy transfer is basically a function of what's upstream and what's downstream. But it can be a nonlinear function. It doesn't have to be linear. And so it allows you to capture dynamics pretty well. I'll show you just a second. Across multiple domains and represent it in a very compact form. Once we actually put this all together, we've got a diagonal capacitance matrix and incidence matrix, which basically is a map of all the edge connections among the different vertices, and some sync and source states. And this full graph model, after we build it up, very good for decomposition into subsystems, which is important for that distributed control that we do later. So as I said, one of the things we want it to be is very sort of scalable. And so we've actually used the graph model approach. You can zoom in to look at this is a power converter. This whole thing here, you could hold in the palm of your hand. And it's a very novel power converter because it uses some advanced semiconductors, wide bandgap semiconductors. These are actually gallium nitride based switching devices, active devices. And we were actually figuring out how the power flows. There's a big heat sink that you have on top of the thermal gap material, the gap pad material. We could actually do a thermal graph model, which shows sort of power flows, and figure out pretty easily, not easily, sorry, pretty reliably, what the temperature looked like at different points on the board, okay, using a very small subset of sensors and some Kalman filtering. But this graph-based representation allowed us to basically discretize the overall system into a set of voxels and then figure out how power would flow through it. So we can go for something that's this small to something that is a bigger. This is one of the ones we'll do the demonstration on. This is a powertrain for a hybrid UAV, hybrid electric UAV. Hybrid electric UAV, this is a class 2 UAV. It's got maybe about a 10 kilowatt motor on there. We can actually represent it as a graph. And this graph here, you can sort of see, we don't have to go through the details of it, just realize there's a bunch of nodes, a bunch of vertices, and a bunch of edges. And it's color-coded to show that they're different domains. We're going to have electrical domains in the green and the yellow. We're going to have thermal domains in the red or pink. And then we've got some mechanical domains in the blue. And after we go through and do all the modeling, if we look at current or voltage on the electrical states, these are all electrical states that we're showing down here. You can see that there's 3 measurements shown and 1 model result. And within the repeatability of the experiments that we do, we're able to capture the behavior of the system very, very well. Same thing on the thermal side. Okay. So why do we like, there are many reasons. One is, why do we like the graphs? One is what I just told you, is that you can actually go ahead and represent the systems and come up with an accurate system representation. That's great. You always want your models to be accurate. The other thing is you can actually use this now to start breaking down a relatively complex system into a subset of simpler systems, so you can actually do control for some of the simpler systems. What I'm showing here is a notional aircraft architecture. It doesn't represent any particular aircraft, and it is just one half of an aircraft. If it was a 10-engine aircraft, where you'd actually have the engine here, some thermal management from an air cycle system. You'd have some fuel tanks. You'd have some coal plates and pumps that you'd use to move fluid around. You'd have some loads that are here, some random loads. And then you might have some mission critical loads and some flight critical loads. Flight critical loads means you have to keep those on. If you don't have those on, the airplane crashes. The mission critical loads are, you have to have those to complete your mission. But if you turn them off, think about this if you're going around on, you've flown on an airplane, the galley, the kitchen, those are mission critical. You want to have those to have a comfortable flight. But if the microwave isn't working in the galley and you can't heat up your meals, you can still get to where you're going. The plane isn't going to drop out of the sky. If the alternator goes out or the generator goes out on one of the engines, and you're no longer able to supply power to some of your avionics or something like that, those are flight critical. You need those. And so that's the difference between sort of flight critical and mission critical loads. I could take a big system like this, and this is actually not that complex for some of the systems that we've looked at. And basically, I can enumerate my power bus from my electrical system that comes off the generator that I have from my engine. The generator also serves as a heat source into my oil loop. And I can actually go ahead and enumerate each one of these, and I can connect it as a graph. Right? What's nice, this is what for this particular example, the graph looks like. We can rearrange it. And one of the things when I do this rearranging, because of the way it's laid out, is I can identify systems by time scale. So I will have certain systems that, like the electrical systems, are very, very fast. Electricity travels much, much faster than heat. And so these would be sort of fast systems, which could be almost algebraic. The thermal systems, these are actually going to be much slower systems. Okay, and so you can start to see a separation in terms of time scale for these systems. And what we can do is you can start to cluster some of the thermal systems together into subsystems and the electrical systems together into subsystems, right? And break this down as sort of a hierarchy of subsystems and systems that go into sort of an overall vehicle system. And I know I'm going through this pretty quickly, but there's a formal way that we can actually do this clustering of the different subsystems. Actually, there's multiple formal ways. What's nice is when you have it in the graph-based form, you can actually do it by time scale if you want. Some of the other things that we've looked at is we've looked at basically like a min-cut method, which is going by the peak power that flows through any given edge. And so if you have strong connectivity with a high peak power, you treat those subsystems together and you don't decouple those. But the bottom line is you can actually take this system and break it down into subsystems formally using some of the graph theoretic tools for graph decomposition. And when you're able to do that, you're able to get it into this hierarchical type of system representation, where in this case, things operate on different timescales. This would be the slowest overall timescale, medium timescale, and the fast timescale. Now notice the fast timescale for the thermal subsystem doesn't have to be the same as the fast time subscale for the electrical subsystems. These are milliseconds or microseconds, whereas these are seconds or minutes. And we've used this for other electrified vehicles. I showed you one for a notional aircraft. This one is a notional hybrid electric vehicle, and it is stuff that we've done with one of our partners here, Ford. And this one, I believe it was decomposed a little bit differently. You can see that there is a sort of component level, a subsystem level, and a system level that is broken down by the electrical system architecture and the thermal system architecture. Right? We've got a vapor cycle system and a cabin system, and then there's a battery system. All this down here is the battery and the motor system. And these are the sort of the electric power subsystems. And this was based on basically what we defined as a distance metric, some type of sensitivity. And there are also agglomerative clustering methods, and you can use different things depending on what you care about to get it into this hierarchical form. But the graph allows you to go ahead and do that. Once you've got it in the hierarchical form, we actually then, the reason why it's nice to do it that way is that you can control the system over multiple timescales. If I have things that evolve, if I have things that evolve at two different timescales, a fast and a slow, I can do singular perturbations and do my analysis on those fine. The problem is, what happens if I have like 4 different timescales? Then it gets kind of hard. Because most of our singular perturbation theory doesn't account for, 4 different timescales are going on. It's just usually a split between 2. By taking this approach, and this is sort of a rewriting of one of the some of the figures that you saw before and abstracting away a little bit, I can have my plant, right? And then I can have specific controllers that interact with the plant. Right? I can have like regulators, which are just maybe embedded controllers, and then higher level decision-making controllers that feed information up to other higher level decision-making controllers that feed information up to controllers that coordinate across maybe multiple different subsystems. Okay. These lower level controllers can be very simple, PI simple controllers. These upper level controllers, we tend to use sort of an MPC approach, and you can sort of see a schematic of an MPC type of controller with this 6-step horizon moving forward in time as you're doing your predictions. What's nice is that for aircraft, at this upper level, commercial aircraft, they fly pretty pre-planned routes, okay? And so you know what you're going to be doing 5 minutes into the future, 10 minutes into the future. If that is unknown to you as a commercial aircraft, you're in trouble. You know what the weather is, you know the direction that you're going to head. You have to hit certain waypoints on your trajectory. And so that actually lends itself well to some type of predictive control. But I will say that the approach in terms of this architecture is agnostic to the algorithm. Right? If you don't want to use MPC up here, you could use something else. That's fine. That's fine. Because it's modular like this, okay, it allows you to use whatever algorithm you want at any different level, okay, and choose the one that's most appropriate for you. Now, the reason why we like to use the hierarchical stuff is because we need it to observe some hard constraints, reasonably hard constraints. A lot of times we'll have constraints on, specifically on the thermal side, which is what I work a lot on. You can't make certain systems go above a certain temperature, or you have to keep them in a temperature range for them to be most effective. The MPC allows you to go ahead and enforce constraints as you're actually going ahead and doing your online optimization. The thing is that if I were to try and use one MPC to control everything, I'd have to pick a particular time step that I use for that MPC. And if I did an MPC and used the fastest time scale for the system, so the lowest level of the hierarchy, I couldn't look very far ahead because I have a fixed amount of computation that I have. Right? I can only calculate so many flops based on my onboard computing power, and I could use those up. Maybe I can only do 10 steps. At the lowest level or the highest resolution and time, that gives me a very short preview. Okay, and so I would not be able to anticipate things coming up further out. If I work at the highest level, I can look further out with most my 10 time steps up here. But the problem is things might happen in between these time steps, and I might not be able to respond quickly enough. So I have this problem of, I can look far, but with relatively low precision, or I can look with low precision, but not very far. Right? And that's why doing the MPC in this hierarchy allows me to solve the problem by basically making the highest level operate slowly and look far, and then communicate with lower levels that are operating quickly, but only looking close in time. Now, one of the things when you start doing these controller designs is you often wonder, well, stability. Is the system going to be stable? Well, and a lot of times for MPC type designs, stability is one of the things that is difficult to satisfy a priori. The classes of graph models that we have here are based on energy conservation, the conservation laws that I showed you. The amount of energy that gets stored in a vertex is equal to the sum of the power flows in minus some of the power flows out. Okay, if I have these energy conservation laws that set up my network, by their very nature, these are what we call passive dynamical systems. They're not going to generate energy internally. They're always conserving energy, obviously, because it's how it's set up, or losing energy. Well, what Justin here was able to show in a couple of Automatica papers was that the power flow along input and output edges amongst the subsystems that form the overall graph. Here are the different subsystems. This subsystem I-1 connects to this subsystem I, which connects to this subsystem I+1, right? And there are connection points and power flows between these two. And by the way, this arrow here doesn't mean it's a directed graph. It just means this is positive, what we consider positive power flow. Power flow can also be negative and come back this way. But the power flow between adjacent subsystems it can be formulated in negative feedback, in a negative feedback form. Okay. Even though these are like, again, this is not a directed graph. That means power can only flow this way, right? It's an oriented graph. This negative feedback here, if each one of these is passive, and I have a negative interconnection, negative feedback interconnection between two passive systems, that is going to be a passive system as well too. And passive systems are sort of by their nature, if you don't disturb them, they stay stable. And so you can actually do an induction on all of the subsystems, right? This interconnection here is going to be passive. So if I've got this passive interconnection and I interconnect it with this one down here with this negative feedback loop, right? Well, that's going to be passive. And so I can show that the entire chain of systems that I have that I've connected to come up with my overall system is going to be passive. And that's great, which means, you know, it tells you kind of the obvious. If I've done this thing with a conservation of energy, overall energy is going to be conserved and it's not going to create energy in the system and blow up. No. So the system is stable to begin with. That's not really the cool part. The cool part was once we realized not just that the system is stable, but because of by the way we've constructed it, it's passive. What I can do now is when I actually design my controllers and attach the controllers to any one of these subsystems at the lower level now, right? If I make the controller itself passive, okay, and I can make it passive or strictly passive depending on the passivity of the underlying subsystems. The underlying subsystems themselves are passive. They're not strictly passive because it's a conservation based. So things are conserved. They're not necessarily lost. The energy is conserved. It's not lost. I have to make the controller also passive to make the overall system passive. And I can play the same game that I did with the subsystems here, where I have the interconnection of the subsystems being passive. So now if I connect the controller to this individual subsystem I, right, if this controller is passive, then overall this system here is going to be passive. And that's great. So if it's passive, it's going to be stable. The way that I make this controller passive, if it's a model predictive controller, an MPC controller, is I can basically put a passivity constraint. Here's my MPC controller, where I'm trying to minimize some cost function, given the system dynamics, where I have some state constraints with some slack variables S sub I here, some control constraints. I put in place this variable here, Z, which is a stored passivity. And what I could do is I could say U transpose Y is less than 0. And that would give me instantaneous passivity. The other thing I could do is when I design my controller is I could introduce this stored passivity variable here and make it sort of like integral passivity. So all I have to do is make sure that as I integrate this term U transpose Y over time, over that whole time window, I end up being passive, less than some value, 0 typically, but doing it this way here, it allows me to violate passivity for some part of the mission or trajectory, okay, as long as I really am very, very passive for the remainder of it, and I offset that loss of passivity at the start. Okay, it's like a slack variable on passivity. It gives you an additional degree of freedom. We did some good hardware in the loop studies, and I'm not going to show you those because I'm going to show you some other results on the UAV system. Oh boy, almost a couple of years ago now, and those came out earlier this year, where we ran the electrical system in software and the thermal system in hardware. And what we're able to do, think about this as a performance plot, a spider plot. When you're looking at multiple different performance metrics, like in your cost function, these spider plots are good ways to represent those. And the blue here is the baseline. And so the closer you can get to the internal square, the better off you are. And what we're able to show is that our approach, our controller, actually performed significantly better. It's got a much smaller area than the overall baseline controller. If we look at constraint violations that you'd have, the baseline controller was a well-tuned. We tried to do our best, but it wasn't predictive. It didn't have the predictive capability at the higher levels. One of the drawbacks to this approach was that we'd assumed full state feedback. On the thermal side of the system, because you can kind of sort of see a little bit of the thermal system layout here. There's a D-space system running the electrical emulator back behind here. The thermal side alone had about 40 states, and the electrical side had even more. And we couldn't measure all those states, right? So we needed an observer to estimate the states. And some of the challenges that we had were similar to the controls challenges. We had multiple dissimilar timescales. We wanted to estimate these states here, which are the thermal states, separate from the electrical states, right? And so we had two options, trying to develop a common filter for the overall system, or develop sort of individual separate common filters, which we call a hierarchical observer. The same way that we did the hierarchical controller, and no surprise, since we'd sort of done the controller in a hierarchical fashion, we did the observer in a hierarchical fashion as well too. And the way this one works is that sort of each subsystem observer sort of estimates its part of the system, and it receives some coupling information from above, and it receives some measurement or pseudo measurement information from below. And so if we looked at this observer here, this observer could be estimating sort of these three plants. But these three here physically in the actual vehicle, they're connected to things that are going on out here and things that are going on out here, right? This takes actual measurements in from here, okay, and starts to estimate things. This one takes measurements in from this one, starts to estimate things. Its estimates of the states, right, are passed up to this controller, right, this observer. This observer is running a reduced order model of the system, of each of these subsystems, right? And in that reduced order model, it has an estimate roughly of what this is doing and what this is doing. And so it passes down to this one what it estimates this one is doing. And similarly, it passes down to this one its estimate of what it thinks this one is doing. And by this sharing of information, you're able to go ahead and compensate for the coupling that you didn't pick up here. At the vehicle level, right, this does the overall vehicle, right? And it receives these, what we call pseudo measurements, because they're really estimates of the measurements that are coming from the lower levels. The nice thing about this is it's got those computational benefits. It's also modular, so if I take one piece of the system out, I don't have to redo my my overall system observer, and it accommodates the multiple timescales that I talked about. So just to show you, there's a couple articles that we had that came out on this, and what we could do for the estimator is we couldn't prove convergence to 0, all right? But what we could prove is we could prove or demonstrate that we could actually bound the errors for each of the observer signals. And those error bounds, it's a sub of a class K function, some exogenous signal, and the coupling effects among interacting subsystems. And you can kind of sort of see here, at least for the thermal system, the blue is the bound and the orange is the actual error that we're able to get off of some sensor probes that we're able to put into the system to actually figure out the actual state. And you can kind of see that these bounds are doing a pretty good job of estimating, of overbounding what the actual temperature error is going to be. And then what you're able to do is you're able to mate each of those estimators to its respective controller. And this is another nice thing about the doing it in a hierarchy. And then you're able to go ahead and run each estimator at its particular time scale, right? So at the top level, you're only running a 17-state observer, updating it every 60 seconds. And it actually works pretty well. This is some experimental results looking again just at the thermal side of things, where this is the estimation of a particular state. Most of them look like that at the top level. And the blue is the estimation, and the red or orange is the sort of actual. It's not actually the model, it's the sort of the actual system. And you can actually see that they actually converge. I think this model here is left over from when we actually did the simulation results. I apologize. You can see that there's this discretization. This is about 60 seconds, each one of these time steps. And there's a bit of a delay in the observer getting started because the subsystem observers have to get started. And so there's a little bit of that delay, but eventually it converges. And what happens is you're able to do a pretty good job of the goal is for the red trace here to track out and trace out the light gray profile. And what this is doing is, the vehicle is running through some profile, and you've got the what we call those mission critical loads for the aircraft. So you have to satisfy these, otherwise you fall out of the sky. And then you've got these additional loads that, if you are going to violate your thermal constraint by not satisfying these, you can go ahead and turn down those loads and just basically make those not available right now until you're able to thermally recover. And you can kind of sort of see that the controller does a decent job. It sheds loads when it has to, just because there's too much power being put into the system. And you're able to go ahead and, on the controller side, these are thermal bounds that you want to stay within. You can see we're sort of staying within the thermal bounds here because the NPC is doing its job. All right. And when you get to this section and you're about to overheat, it says, no, so it turned down the least critical load that I have, and I shed that load, and I'm able to sort of stay underneath that bound. Just to make the point about why we did a hierarchical observer versus the centralized observer. If we were to do a centralized observer where we ran the Kalman filter at that 2-second time scale for everything, you actually do pretty well. You do actually much better in terms of your overall estimation errors. Right? The average estimation errors is very small compared to the estimation errors that you would get at different levels of the hierarchy. Right? At different levels of the hierarchy, this is at the highest level of the hierarchy, your estimation errors can actually be quite high. They can be 10 times bigger than the estimation error for the centralized observer. At the lowest level, where there's very little of that coupling and pseudostate activity going on, you do very, very well. Okay, but as you go up, your estimation error gets worse. The centralized actually stays pretty low throughout, and you can kind of sort of see what we were talking about in terms of there being multiple timescales involved, and why you can't just do a singular perturbation type analysis, because here there's 4 of them. The problem with the centralized observer is that if I actually run the Kalman filter for the centralized observer, that can take a little bit longer to calculate. And so when I put it into my controller, there are times, each of these arrows here, are when my controller actually doesn't get the information it needs in time to perform a calculation. Right? The combination of the observer and the controller takes too long to calculate before the next time step shows up for it to execute. And at these points in time, the default is, if I don't have the right information, is to sort of set everything to 0 and wait for a good piece of information to come in. Alternatively, we could go ahead and just basically keep the last thing that we did as our control signal, and that's fine too. But the point is that I actually run out of time to calculate my control signals if I do this centralized type of an approach. So the where this actually has been used, and we showed you some. I'm not going to show you the video here, but this is a UAV. This is a hybrid electric UAV. And if I actually do a hybrid electric UAV, I can actually increase my range a little bit. And this is what it looks like. This, I referred to this a little bit earlier. The powertrain of this, you can see there's an engine here. There's something that emulates a motor and a propulsive load. There's a whole bunch of electrical loads on here. These can be pre-programmed with a DSpace system to emulate different types of avionics loads. And I can represent this system. This is where the graph would come in to represent the subsystems very easily. I can represent the converters, the heat exchangers, the fluid tanks. Each one of these I can sort of modularize and develop individual models. And then I can actually bring those together. So each one of these would be a separate model. There's some tricks that we use from graph theory to automatically compose those and come up with a graph of the system. I can then go ahead and execute my MPC that I did before, where I've got my electrical system, and I've got my thermal system, and I've got my mechanical system. The mechanical system coordinates a lot with the electrical system, electrical mechanical system. And as I said before, we're going to use the PI controllers just for the low-level mass flow rates of my pumps and everything for my cooling system. MPC for tracking wall temperatures, and the upper-level MPC for doing battery state of charge and load planning, things like that. For the sake of time, the overall system has about 70 states. I just want to go ahead and focus on the electromechanical piece. And what we'll have is the battery state of charge, load and component planning, and then vehicle speed, reference tracking, and the genset coordination that goes into how I control my speed of my motor and my genset, like this. The controller performance evaluation will look at how well I'm tracking my speed of my aircraft as I go up and down. The reliability objective is basically how well I stay within some of my constraints. And then the efficiency objective is how much fuel am I using. And doing everything that I said before, we can sort of see the effects of this distributed hierarchical architecture. I'm going to speed up just a little bit and sort of just focus on one of these things here. You can see one of the things that's happening. There is the total load, the avionic load, happens to comprise sort of a baseline load plus some periodic load that's added to it. And this is just sort of faked. I'm not going to put an actual load profile up on here for proprietary reasons. But suppose that all of a sudden my base load went up and my base load then came back down. My base load comes back down here, right? What would happen is that my engine's producing power to meet this load, but all of a sudden that load drops, but my engine is still producing power. If I am not careful, if I look at the battery current down here, when this drops, right, the battery current goes negative, very, very high negative, and you're trying to absorb all of that release or lack of demand for energy into the battery, which means the battery is actually charging, and the battery has a constraint. The battery only wants to charge at 10 amps. Right? Negative battery current means that current's flowing into the battery, and so I don't want to charge fast more than 10 amps. If I overcharge the battery, you'll degrade the battery. You can't use it very long. You'll damage the battery. And so you can see for sort of a baseline controller, I actually violate my constraint significantly. But for my hierarchical MPC type controller, it's able to start to take action beforehand. And so when this shutoff comes, it just rides that constraint very nicely. Okay, and so you'll be a lot more proactive in your actuation. And if I look at sort of the fuel consumption over a baseline, because it does a little bit more of a charge depleting, not as much of a charge sustaining, I do about a 10% better. Here, shorter is better. And in all sort of the metrics that we would show, the hierarchical approach does actually a fair bit better. And the experimental results look almost exactly like the simulations. The first were simulations, and the second were the experimental, and you can't really even tell the difference. It just shows you how well the models capture the system behavior. I want to wrap up real quick with design. And here's an example of why you might want to do design for things like, if you've heard of Uber Elevate, eVTOL aircraft. A lot of people are scrambling to try and figure out how to go ahead and do the eVTOL design. The question, a lot of times the control folks get given the plant, and the plant is given to you. The idea is, how would you change the plant, right? If you wanted to go ahead and come up with the best plant to control. And we've asked that question for a while, but we haven't done too much of it as a community. So how do you optimize the physical design while also optimizing the control strategy? That's what we're after here. One of the things that's nice is that if I change the system, it's kind of equivalent to changing the graph. One of the things I can do is I can change the size of a vertex here, right? Or basically the power flow along an edge. And so this is the equivalent of basically upsizing, my battery, changing V4, the size of it. I can also adjust the topology of the system, which is the same thing as adding or removing an edge. So, maybe I don't need this. This is like an auxiliary motor. I want to get by with 2 motors instead of 3. I basically remove those 2 edges. Right? What's nice is this graph-based model, I can augment it with a couple of matrices here. I can augment it with these sizing design matrices and these topology design matrices and put those in each of the elements for this previous kind of state space model that I had before earlier in the talk that talked about CX doc negative M times P plus D times P in. And these psi type variables figure, whether I actually size these things. These phi type variables say whether or not I actually add or remove these things. And now it's a relatively compact form, and it's a pretty easy relationship between design variables and the graph-based variables. And now I can actually do a search along this matrix, right? This is a diagonal matrix. So if I want to get rid of certain things, I actually just basically zero them out in this phi type term there. And I'll give you an example of what I mean here. I'm wrapping up here. I know I'm running a little bit late. If I look at a hybrid energy storage system where I use a battery and an ultracapacitor to provide both high energy density and high power density to some load, okay, and we're going to look at the electrical aspect here. We won't look at the thermal side. The question is, for a given load that I have to satisfy, what's the right mix of ultracapacitors and the right mix of batteries to satisfy this load with a minimal weight? Well, we can go ahead and build up a model for that hydroelectric energy storage system using sort of a battery set of graphs connected to a converter and an ultracapacitor connected to a converter that all feed some voltage bus and satisfy some load. For the sake of discussion, each of the individual subsystems, the battery and the ultracapacitor, their controllers are going to be simple PI controllers that work well. And you can see that even if I have a pulsatile load on my system, the controllers are able to go ahead and keep my voltage within a couple volts or a half a volt, even though my current is swinging a fair bit just with these simple PI controllers. And this system can be represented in that form that we just talked about, that CX dot minus MP DPS. Then I can augment it. Let's not do topology here. We're just going to do sizing. So these are the sizing variables that we're going to add to each of these, right? And each of these sizing variables, right, we consider these to be these design matrices that are, in this case, diagonal, where I can actually set these weights, right? And changes these weights basically changes a design variable on a vertex or an edge. The things that we're allowed to change here, right, in terms of these weights will specify the physical design variable in terms of the number of ultracapacitors that we have in series or parallel and the number of batteries that we have. We fix the topology of the batteries to be parallel. As well as the controller gains that we would have for the PI controllers for both the battery and the ultracapacitor. We can go ahead and put that into an overall multi-objective problem where we're trying to basically weight whether we care more about size or whether we care more about performance. And the cost function and size basically is the mass of the overall combination of batteries and ultracapacitors. Capacitors can be a little bit lighter than batteries. Versus whether or not I actually deviate from my bus voltage very much. We can also add constraints to our optimization and then throw it into our favorite numerical optimization tool. Many of these types of systems so far tend not to be very convex, and so gradient methods don't work so well. So we have to use some other type of non-convex optimization tool. But at the end of the day, you can come up with some nice results that show that, if I do the sizing optimization with a fixed controller, I can actually find an optimal Pareto front that dictates whether or not the best combination of caps and batteries for a given duty cycle that I would run through. As it turns out, if I go ahead and add my controller optimization the same time I'm doing the design optimization, I can actually shift this Pareto front even closer to an ideal point. And here is a test case that we'll sort of show on the next slide, which shows that just with some weighting on how I weight size versus performance, so it looks like I'm weighting performance a little bit more than I'm weighting size, I'm able to comparing the initial design in blue and the final design initial design in red and the final design in blue, the final design ends up being about 50% smaller than my initial design, okay? And with a very different makeup here. So we've got way more batteries, right, than ultracaps. This is fewer, the original design had started off with more ultracaps and fewer batteries. We went to more batteries than ultracaps as a percentage of the overall system. But we found that with more battery percentage, we could shrink the overall system. The batteries are actually pretty good at providing a lot of the load, and the ultracaps only had to do a slight little bit, while also improving the deviation from the reference. You can sort of see that. And along a bunch of other metrics, you can actually see that the optimized co-design outperforms both the initial design in sizing and the performance objectives. So in conclusion, hopefully I can convince you that the controller development for these complex systems, it really starts with that graph-based approach for us. But if you have your other approaches that are modular and scalable, that's great. Go ahead and use those as well too. And I like to say the architecture first, then the algorithms. If you get the architecture for the problem right, which includes the modeling that you use, it makes figuring out which algorithms you're going to use downstream much, much easier. If you start with, I've got this algorithm, this is my favorite algorithm, and I'm going to use it on a given system, it does great for developing the algorithm, but when it goes to actually implement it on a given system, you might run into problems, okay, if that system doesn't happen to be one that is naturally attuned to that algorithm. The graph-based approach, what's nice is that actually you can cluster things and to create these hierarchical models. The hierarchical models integrate well with hierarchical controllers, and those hierarchical controls allow very good coordination amongst very disparate subsystems while achieving the system goals. The hierarchical observer also helps in terms of estimating information at different timescales as well too, and it does a lot better than simple local or decentralized controls. We don't say which control approaches you have to use for the algorithms, and we completely acknowledge that a wide variety of approaches can be examined, but keeping this overall framework in mind, I think is going to have a lot better approach of success than most others that we have seen to date. So with that, I'd like to thank the students here who have done much of the work, as well as the sponsors over the years who have worked with us. And I will turn it over to questions. And I know.
All right, Andrew. Fantastic talk. I really enjoyed it, and a lot of system perspective here. Just not the control, but everything else that counts. Is there anybody that want to ask any questions? We don't see anything on the chat box though, or in the question answer.
Don't see anything so far.
Right. So, well, if not, then let me get started.
Sure.
So, what kind of algorithm do you use inside MPC?
In what
MPC,
sense?
you use some in the computational sense, basically, right?
Yeah. So we will use sort of prepackaged solvers that we will use.
Okay. What solver typically?
Yalmet was one that we'd used a fair bit. Jirobi was another one. And there's a third one that the students had used as well too, that they found was pretty good at solving things online. But Yalmet and Jirobi are the two sort of standard ones that we fall back on in terms of numerical optimization tools.
And what language it's written? Is it in C or something like that?
Oh, these are our toolboxes that exist in MATLAB.
Okay.
Yeah.
So you go for the Simulink sort of thing, and then kind of generate the C code out of it, and then rapid prototyping, right? That's what you do basically. Isn't it?
Yeah, and in some cases, for some of the really what you will call it, for some
Sajid, can you mute everybody?
Can I unmute them? Is that what you're saying?
No, it's a mute everyone. If somebody wants to talk, they can talk, because a lot of background noise. Just leave the background here, and only participants. You just put everyone muted.
There you go. I think we got it now.
Okay,
yeah.
got it.
Sorry.
Yeah.
You were talking about in some cases, what we can do is early on for like the longer time scale things, if I have like a minute or two, I don't even have to go ahead and do the real time C code generation. For some of them, I could actually, they'd solve fast enough. I could actually import it into MATLAB Workspace, chunk it all around in the MATLAB Workspace, and then export it back. And it wasn't hard real time, but it would execute within the window, the 1 minute window, that it was sufficient. Yeah. Once we went to the smaller time scale ones, the shorter distances, then we had to do some of the stuff that you're talking about and do the real time code execution. The other thing that we've done before too is for some of the simpler problems is that we've hard coded it, so we've turned it into like a lookup table, kind of like a fast MPP. Okay. And then once you have that lookup table, you can embed that and turn it into decisions that you would see.
Got it. Yeah.
So that's worked too. Oh, someone coming in.
Yeah, we have two questions.
You indicated the use of GaN semiconductors for power electronics. Oh, excellent question. How do you see the impact of silicon carbide in the future? So I talked about the GaN. I think for the electrified mobility, the silicon carbide is the way to go. This is from Jayesh. The silicon carbide, you're going to see that way before you're going to see the GaN for power applications. I think for mobile power applications, you're going to see that, and we're starting to see that already. For some of our traction drives that we have for cars and for large sort of off-highway applications, the silicon carbide is better, just because some are better at voltage and some are better at current producing. We started off looking both at the GaN and the silicon carbide for power conversion applications. And over time, with some of our suppliers, we've sort of dropped the GaN because it's not gonna work in the market. And we've pushed forward with silicon carbide. We're actually going to be flying within POETS. My colleagues at Arkansas. There's a company called Ampere. You can look it up, AMPAIRE. It's an aircraft where the front engine, I think, is a gas engine and the rear propeller is going to be electric motor. And and they're actually going to be flying a silicon carbide based drive on that aircraft that they're looking to go into production with sometime next year or two. So I would actually bet for the electrified mobility space, the electric vehicles and stuff like that, you'll see silicon carbide in that domain. The drawback to silicon carbide right now is the price. It's still more expensive than silicon. And so a lot of the auto manufacturers or the folks that we've dealt with in the off-highway, they're trying to see how far they can push silicon, right? But it's a great question. I think silicon carbide is going to make a big play. It's going to be there.
I think there's another question on the nonlinear dynamics aspect. Are you designing your controllers based on nonlinear dynamics or even the MPC part?
Great question. I think that the graph models they are actually we do the linear dynamics and static nonlinearities. We haven't found a good need to do dynamic nonlinearities because we can capture most of the behavior that we want in the static nonlinearities that the connections between the dynamics and the vertices, but each of the vertices are basically like just single integrators, and we found that is actually pretty good for capturing most of the types of systems that we would see. And all of our, these are actually being used in a lot of organizations and companies now. Once they've seen this as a way to pick it up, a lot of them are actually using this sort of internally, and with very good results. Usually you're within a steady state, you'll nail it. In transients, you might be off by 10-15%, but for the controller design, for early stage architecture understanding and the behavior, it has been very positive. And the time it takes to build one of these graph models with that constraint of linear nodes and then nonlinear edges, it's been surprisingly fast for people to pick it up and go from like a wiring diagram to a functional model.
So I actually have a question. So the way I understand it is you presented a design approach, right? A system level design approach for both optimization and controller design.
For the plant, yes. Yep.
I mean, given that we've had hybrid electric vehicles for a while now, like Toyota has had its Prius for many years, right? Especially in the US. Like the data that you got and the experimental data that maybe Toyota could share with you, like were you able to reproduce the results?
For design optimization?
No, or with the with whatever components that Toyota has selected, and like if you use those in your the graph-based model, are you able to reproduce the same field testing results that Toyota may have obtained?
So
like, sort of like the ground truth, if you will.
Two things. I think I understand where you're going, and that would be how much faith could we have in the models if we used real data.
In a way, yeah.
In a way, yeah. So Toyota would not share their ground truth data with us because it's still proprietary. Within the center, Toyota was there, GM was there, and Ford was there. So they're not going to actually share the actual ground truth data that they have in any of their vehicles, just because their competitors are also there, and everything we do is pre-competitive. What we have been able to do with, for example, like Ford, when I showed just one picture of a hydroelectric vehicle, we took the parameters that they gave us, and they said, these are not our production parameters or representative of anybody's productions, to try and have disclaimers. But the results that we're able to get coming out were, when they ran it by their engineers, they said, yeah, that looks reasonable. That looks like about right.
Okay, great.
Yeah.
Well, the next question, I think, again, there is a question from Joyce, but Joyce is now a panelist. So, Joyce, can you unmute yourself and ask the question? Joyce. Joyce is okay, part of our EXCOM member in the Bangalore Control System Society. Joyce, can you ask?
I did unmute him.
Joyce, can you ask a question yourself? Can you switch on your video also if you want to?
His audio may not be connected because I don't see an audio icon.
Yeah, I know. I don't see that either.
Okay.
But
then I can read it out.
You go ahead and read off.
Multi-rate MPC. His question is on multi-rate model predictive control. And you have multi-time scale systems. Any thoughts on how multi-rate MPC can be used?
Can you see advantages of hierarchical MPC for multi-time scale systems?
No, we can see advantages of, we can see the advantage, but any thought about using or operating multi-rate MPC? That's his question.
I believe so. Any answer that you give as an engineer, either an engineer or a lawyer, your immediate answer should be it depends, right? Because it's always going to depend. If it's like a candidate problem and the problem is fixed, I could see using multi-rate MPC. Absolutely, right? And you could get a controller that would work. Yes. The reason why we, instead of having one multi-rate controller, having multiple controllers that communicate, a lot of that is driven by the type of problem that we work on and the people that we work with. A lot of times you will get a subsystem, like you won't get control of the whole system, right? You'll get a subsystems where you're able to like maybe feed them references, right? So someplace like Honeywell, they're going to sell their packaged thermal system to Boeing, right? And they've got their own controller that they've built in that then has to go into Boeing's aircraft. Boeing may be able to go ahead and sort of give references to that system. They may not be able to have the overall sort of MPC at that level. They may have to take whatever the performance is. And sort of breaking up, like I said, into multiple controllers gives you that modularity. Right? And it's one thing, like a controls person, you might think, yeah, but that's not very effective. Why don't I just go ahead and take control of everything? Well, from a IP perspective and a competitive perspective, business-wise, it is a good idea to keep things sort of walled off and it's a black box. It hinders the overall engineering efficiency, but from a business perspective, it makes sense because each of the people that sells the black box can sort of wall off their business and protect it from other folks. And it's a reality that we've run across. But to your question, absolutely, you could use a multi-rate MPC if you had a fixed problem.
Thanks a lot. Joyce, do you have any other thing? I mean, you can unmute yourself now.
Can you hear me? Can you hear me now?
Yeah. Yes.
Okay, yeah. Thanks, Andrew. Yeah, I think I could get your perspective because the subsystems here are owned by different suppliers. So it makes sense because each may have their own controls. So it might be good approach to look at a hierarchical way. But yeah, my question was more from technology perspective because in hierarchy, sometimes you lose on coupling or interactions, whereas using single centralized multi-rate MPC can help you avoid those. But yeah, as you rightly mentioned, while decomposing, you are talking about communicating some of the coupling coefficients, and that may be a way to solve. But again, because subsystems are from different players or suppliers, you need to ensure that those coupling coefficients or coupling parameters are communicated between multiple subsystems. So that would be a practical requirement, right?
I agree.
Yep.
I agree.
All right. Fantastic. I don't think any other question there. So
I do see one here. And it came in.
Okay.
It looks like it didn't come in to everybody. but it asked, what are the challenges for motor drives in improving efficiencies with respect to materials and electronics? It wasn't sent to everybody.
Okay.
Yeah. So I'm trying to figure out what I could say that's not proprietary. Because a lot of the stuff about the ARPA-E type stuff where people are going after this is proprietary. One of the challenges for the motor drive with respect to efficiencies is exactly what somebody else brought up earlier in terms of silicon carbide or gallium nitride. Either way, getting away from silicon and going to higher switching frequencies will help, right? Because with the higher switching frequencies, you can increase the efficiency. You have to work on some electromagnetic interference issues at the higher switching frequencies, but you can gain efficiency. And when you sort of gain efficiency, you should also be able to minimize the thermal load, which means you can downsize your thermal management approach. So some of the motor drives, in terms of materials, the wide bandgap materials, from a purely technological perspective, that will be one of the things that you could use. Unfortunately, it's going to increase the cost right now, but this is not a cost-driven thing. It's sort of a technical thing. The wide bandgap. The other thing you could do is you can actually do a better job of integrating the thermal management with the electrical system. Many of the early systems, if you've ever seen the EFAN, the system that sort of flew over the English Channel, that was electric driven system, they actually use liquid cooling. Liquid cooling is heavy. If there's a way you can do this with air cooling, it would really help. It would really help. But that means you have to reformulate the architecture of your motor, right, to accept so you get the air cooling. The other thing too that you want to look at is, can you get electronics that actually operate at a higher temperature? That's the other thing that some of these wide bandgap materials can do. Instead of having the 170 degrees C max temperature, 150 degree or 120, whatever it is for silicon, can you go over 200? Can you go over 250? Usually the breakdown there now is in the capacitors. So can you get things like aluminum nitride based capacitors that can still get you the energy density that you would with some other capacitive type materials? And this is part of that overall sort of systems problem that we're talking about. So you got to solve one piece and then another piece and another piece to try and get the overall system to get it down and get to that 16, 17, 18, 20 kilowatts per kilogram.
All right, I have a natural curiosity, Andrew. So the avionics, the aircrafts actually typically fly at a high altitude and a little bit higher up in altitude. And then the air is very cool, pretty cool out there, right? In the higher altitude. Does it really help, or it's not sufficient enough?
Great question. It's higher, it's colder, it's thinner. It's thinner. It's lower density.
Density is low. Yeah. So
it's the ability to carry away heat is actually less. The other thing too,
you can compress a little bit, right? I mean, you can compress the air, right? A little bit.
Which takes energy. But So it's colder, it's thinner. That's one thing. The other thing though, and here's one of the key things in earlier aircraft, like your 767, even the 777s from Boeing or Airbus, the older ones, they were aluminum, right?
Right. Yeah.
Aluminum skin. Like the newer ones now, the 787 and what is it? The Neo, the 330 or something like that, from Airbus. They're most of them are going to composite, at least the wings, but sometimes the overall systems are composite. So you actually have a hard time getting the heat out apart from just some dedicated heat exchanger places. And if you go look at, it's usually at the wing root. If you go to a new aircraft, you can actually see there's a little hole by the wing root where the wing comes into the body, and that's where the heat exchangers are. If you have big heat exchangers, that adds to the drag of the vehicle. So that reduces. So they want to make those as small as possible, and you can't get heat out through the skin. because it's this composite polymer that doesn't let the heat out very easily, and so that's what's sort of driving some of the challenges. Like that. Remember the Boeing 787 when it got grounded because of the battery fires?
Right.
Part of it
Right.
part of it was the electrochemistry and the damage to the battery, but part of it was you actually, once it started to build up heat, you couldn't get the heat out of there, and so you got this runaway reaction, and that grounded this. That cost them a lot of money.
Got it. Yeah.
So your point is quite well taken. Up there it could be a benefit, but it's still a challenge. Just operating in the colder environment doesn't. And the other thing too is, here's your colder environment, right? And you've got all these layers of stuff. Here's where the heat is being generated at your active devices, your switching devices, and there's a long way between here and here. If you're putting in a lot of heat, 50 kilowatts here, you better figure out a way to manage it right here. Otherwise, this part's going to fail before you can ever get a chance to get it out.
I agree. I completely agree with that.
Yeah. It's a pretty cool systems type of problem, overall problem.
Yes, certainly.
Yeah.
Is there any other question from anyone? I don't see it here in the chat box or in the question answer. Is there anyone direct question to you? Not really, right?
I'm looking. I don't see any others. No, not see any others.
All right. If not, let's conclude it here. I mean, we really enjoyed the session. It was very good eye-opener for all of us, and we'll continue to interact with you in future. So
I appreciate you.
I have never met you in person, but pretty soon probably we are going to meet in person as well. Most welcome to come to Bangalore as well. You have seen the northern part of India, but you can also see the southern part of India. It's a different one.
I never thought I would say this.
It's kind of a little Europe out here.
Okay. I never thought I would say this, but I look forward to the day when I can get back on an airplane.
Yeah.
All of us. Same here.
All right. I mean, we'll not lose hope. I am from aerospace. I'll not lose hope here.
That pandemic.
Thanks for your talk. Thanks very much.
Yeah, thanks a lot.
Thanks, Andrew. It was excellent talk. Very nice. Yeah. Thank you so much,
guys. Thanks so much.
We'll meet pretty soon in the IEEE BOG meeting anyway.
Hopefully in person one of these days. I want to do
it. Next one maybe.
We can travel again. All right.
Bye. Thanks again.
Have a great weekend.
Bye. Thank you.
Take care.
You
Bye.
too. Thank you.
Thank you so much. Yeah.
So I'll end the event for all. I'm the host.
Yeah, Sanchit. Yeah.
Okay. Thanks.
Yes, Sanchit. Thanks.
Yeah.
Thanks.
Bye.
Yeah, it was good. Bye.